Okay, guys, welcome back. Remember, in previous lectures, we have discussed conduction heat transfer and we restricted our discussion to steady state heat flow. Means the operating conditions do not change with respect to time. So, today we are again uh, c- discussing conduction heat transfer, but in this case now we are also going to include heat generation source inside the system. So initially we will consider a plane wall in which there is a heat generating source. Now you can see in this figure that there is a heat generating source inside the wall. Example of heat generating source can be, for example, there is an electrical resistance passing through the wall inside, and which is generating heat. Remember, heat generation is a volumetric phenomena, and its unit are watt per cubic meter. So the wall is having a total thickness of 2L. The temperature at the center of the wall is maximum due to this heat generating source, and we have represented this maximum temperature by T naught, which is at x is equal to 0. Remember, x is equal to 0 is the center of the wall. Now the two faces of the wall are maintained at temperature Tw. What we are going to do is that we will establish an equation for temperature distribution. Remember, we will consider constant thermal conductivity. We will just study one dimensional heat equation, and in this case we are interested only in x direction. We can also say that in this case temperature is a function of x only. Now we have derived conduction heat equation, and you can see this equation is a simplified version of the equation that we have derived. Now in this case you can see that there is no time factor involved because this is a steady flow case. Q dot is involved because uh, this is a heat generating source is inside, and thermal conductivity K is out of the derivative because we are treating it as constant. So uh, first we have to do is that we need to find a general solution for this second order differential equation. In order to find general solution for the second order differential equation, we need to integrate it two times. So okay, so uh, before integrating this equation, let's discuss some boundary conditions. By looking at the geometry, we can uh, say that boundary conditions are that, for example, when x is when we are at distance L, or we can say when x is equal to L, the temperature of the wall is Tw. Basically, it is that region. Uh, uh, it is basically the face of the wall, and we can also say that when x is minus L, temperature is again Tw. And the second boundary condition is that when x is equal to 0, we are at the center of the wall. Temperature of the wall is maximum temperature, which is equal to T naught. So we need to integrate this second order differential equation two times. After first integration, we get this equation, which I have double checked. Then after second integration, we get this equation. Now you can see there are two arbitrary constants c1 and c2. We need to find value of c1 and c2. That we can do by using boundary conditions, which we have discussed. So boundary condition number one is when x is equal to L, temperature at the face of the wall is Tw. Or we can also discuss boundary condition number one as when x is equal to minus L, temperature at the face of the wall is Tw. So putting this boundary condition number one in this general solution, which I have labeled it as equation A, we get this equation B. Now solving this equation equation B and C, we get value of constant C1, which is equal to 0. So constant, arbitrary constant C1 is 0 in this case, and this we can do it by using boundary condition number one. So we can say that boundary condition number one has two parts. Boundary condition number one has two parts. Part 1 is when x is equal to plus L, temperature is Tw. Part 2 is when x is equal to minus L, temperature is Tw. So using boundary condition number 1 for the first part and for the second part, we can find value of arbitrary constant C1, which is equal to 0. Remember, you can subtract equation B from equation C. You can also get arbitrary constant C1. And now putting boundary condition number 2 in the general solution. Remember, general solution is our equation small a. So putting boundary condition number 2 in our general solution, boundary condition number 2 is at x is equal to 0, temperature is maximum temperature, and we get arbitrary constant C2 equal to T naught. So putting the values of arbitrary constants C1 and C2 in our general solution, we get equation G. So equation G basically tells us about the nature of the curve, the nature of the temperature profile. You can see here that x square is involved, so we can predict that the profile will be of parabolic nature. Now if we put or replace x by L in this equation G, so we already know that when x is equal to L, temperature is Tw. So this equation changes into this equation H. Now if we divide equation G and H, we get this equation. So that was the equation what we were looking for. From this equation, if we know maximum temperature which is at the center of the wall, and if we know temperature at the face of the wall, we can easily find temperature for any value of x. We already know from energy balance that heat generated inside will be lost or conducted to the faces of the wall. And since we are dealing with steady state case, so we can say that there is no changes in internal energy of the wall with respect to time. So we can write this energy balance as this is heat conducted to the faces of the wall. This is equal to heat generated inside the wall. And this equation we have already discussed. What we can do is that if we want to use this equation, you can see here there is temperature gradient involved. So if we differentiate this equation with respect to x, we can find temperature gradient for this equation. We will put temperature gradient in this equation. So rearranging this equation and then finding temperature gradient, remember we will take constants out of the different derivatives and we can find temperature gradient. So temperature gradient dt by dx comes out to be this equation J. After performing differentiation with respect to x, we can find temperature gradient dt by dx, and then we can put it in the energy balance that we have discussed in our previous slide. So by that way we can obtain equation for temperature distribution. Now there is a question for you guys that the heat generated inside the wall is conducted to the faces of the wall. Now the heat conducted to the faces of the wall will be now uh, convected to the outside fluid. So if there is any outside fluid uh, in which the wall is exposed to, then the heat conducted is equal to heat convected to the outside fluid. So I I expect you guys to establish equation for that. Now what if our geometry changes to a cylinder? For example, there is electric wire in which current is passing to the center of the wire. So heat is generating at the center of the wall. For example, the cylinder or the wire is having uh, radius equal to capital R. Remember, again, we are just concerned with one dimensional conduction heat, and in this case, uh, the heat direction is along the radial direction. So temperature is a function of radial direction only. So this is the equation for one dimensional conduction heat equation for cylindrical system. Remember, we are dealing with steady flow case and we are taking thermal conductivity as constant. Uh, if you remember, this equation, derivation of this equation was your home assignment number 1. So what are the boundary conditions for this case? The boundary conditions are at R is equal to capital R, which is the radius of the cylinder, and we are basically at the circumferential surface. The temperature is equal to TW. So basically this is the temperature at the outside surface of the cylinder. Now that we have discussed that heat generated inside the cylinder is equal to heat conducted to the outside surface of the cylinder. Remember, heat generation is a volumetric phenomena. So in this case, we will multiply Q dot with volume of the cylinder. And you can see this is Fourier's law, but for cylindrical system. You can see this 2 pi RL is area involved in this conduction heat transfer. We can rewrite this equation as this by rearranging it by taking this Q dot by K to the right side and multiplying both sides by this R. We get this equation, and from the product rule of differentiation we can rewrite this equation as this, which I have closed it in a box. So what we have to do now, again, we need to integrate this equation 2 times to have a general solution for this second order differential equation. And again, our objective is to have an equation for temperature distribution of this cylinder. So integrating this equation one time, we get this equation. Remember, after first integration here, constant C1 is not involved, is now involved. So what we need to do is that we should put boundary condition number 1 after first integration. What is boundary condition number 1 in this case is that when we are at the center of the cylinder, R is equal to 0 and temperature is maximum temperature. We can also say that at the center temperature gradient is 0. So this is basically the boundary condition at the center of the wall. So after using this boundary condition, we get C1 is equal to 0. Remember, we have integrated uh, the differential equation one time, and then we have used boundary condition at r is equal to 0, and we get arbitrary constant c1 is equal to 0. Now boundary condition number 2 is that when r is equal to radius of the cylinder, temperature is Tw. This boundary condition we will use after second integration. So after performing second integration, integration, and putting boundary condition number 2, we get this equation. So after performing second integration, our general solution is this, and then putting boundary condition number 2, we get this equation. So what we have done after second integration, we have already found that c1 is 0, so this term is 0. By using second boundary condition at r is equal to capital R, temperature is Tw, which is basically this equation. So in other words, we have found value of arbitrary constant C2, which is equal to Tw plus Q dot R square divided by 4K. Now the final solution for temperature distribution is given by this equation 2-25a in the book of J.P. Holman. How we got this final solution for temperature distribution? This is that we have used arbitrary constant C1 and C2, and putting the values of arbitrary constant C1 and C2 in our general solution, we get this equation. Now we can rewrite this equation in various forms. For example, we can rewrite this equation 2-25a as this equation, similar to the one that we have discussed in case of plane wall. Now you can see that when R is equal to 0, temperature is T naught, and this equation changes into this form. We can also discuss this heat generating source for a special case. For example, if you have a hollow cylinder, if you have a cylinder with some thickness and it is hollow, so by using same procedure, we can have values for arbitrary constants C1 and C2, and then we can find equation for temperature distribution.